Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on a case study for modeling heteroscedasticity. And in this lesson, I'll introduce a case study along with exploratory analysis. The case study is on foreign exchange rates. Foreign exchange is the conversion of one country's currency into that of another. From the economic theory point of view, over long periods of time, exchange rates between two countries are set in a way that they will tend to offset the differences in inflation rate between the countries. In other words, in an efficient international economy, exchange rates would give each currency the same purchasing power in its economy. This is called the principal power parity. For this analysis, I selected to analyze the exchange rates between the US dollar and three other currencies: the euro, which is a currency in the most countries in the European Union, Brazilian real, and the Chinese yuan. The exchange rate between US dollar and euro should best reflect the principal power parity theory. Brazil is a developing country, and hence there may be some frictions in terms of the exchange rates due to political instabilities. Last, I selected the Chinese yuan because of recent debates on currency manipulation. Generally, the study of temporal dependencies in exchange rates can also be used for forecasting daily fluctuations in rates for investment. Large contracts between countries can be placed given the level of exchange rates. Moreover, investments in a country are also highly dependent on the volatility of the exchange rate with the currency of that country. Data for the exchange rate between euro and USD is available only since 1999 because it was introduced in the market in January 1999. Data for the daily exchange rate for Chinese yuan is available since 1999. At least this is the data I was able to find. And I only found daily data on the exchange rate for the Brazilian real starting with 2000. A first step is to read the data in R using the read.csvr function. Each currency rate is provided in a separate and an individual file, but all files have the same structure, and hence the R code in this slide applies to other two currencies, but although it is for euro only. To note that I'm using here yet another R command to process dates, which is different than other commands used before. This is to show you that there are many R functions to process time series data. The code on this slide also provides the R lines of code for plotting the time series data along with the one-order difference time series. The time series plot for the three currencies are here. The exchange rate between USD and euro starts at a rate of 0.84, meaning 0.84 euros for $1, and continues to increase in favor of US dollar, reaching a level as high as 1.25 in August 2000, then slowly decreasing over a long period of time with large volatility. Interestingly, at the end of the period of the study, the exchange rate reached a similar level as the rate when euro was introduced. Similarly, the rate between US dollar and Brazilian real had ups and downs, varying over a much larger range than the exchange rate between US dollar and euro, pointing to higher volatility and hence higher risks. Last, the exchange rate between US dollar and Chinese yuan has a surprising pattern. For many years, the exchange rate presented little variation and change until January 1994 with a big jump, with a big change, beginning of year 1994, then showing again low variation and change until 2007, then slowly decreasing until end of 2015 when it started to increase again. Differences in the volatility are better reflected in a difference time series. Their plots are on this slide. The smallest volatility is for the currency exchange between US dollar and euro. For this exchange rate, we see some clusters of high volatility, but also an outlying volatility in 2004. We observe a similar cluster volatility pattern in the exchange rate between US dollar and Brazilian real, although the volatility is several folds larger. For the exchange currency between US dollar and Chinese yuan, there is an extreme value in 1994 thus the volatility is hard to evaluate because of this outlier. These plots show, these plots are for, again, the difference time series, but rescale in a way that all three plots have the same scale. They show, again, the difference time series and across all three currencies. Once the outlier in 1994 for the Chinese yuan is removed, the largest volatility is now for the Brazilian real. In comparison, on the same scale, the volatility for the exchange rate for the euro is quite small. However, for the Chinese yuan, we identify periods with extreme small changes over long periods of time, but also periods of high volatility. Extreme small changes over long periods could be interpreted as control over the currency purchasing power. However, we do note that the volatility in the exchange rate for the Chinese yuan is larger than for the euro in recent years. Next, we will assess the autocorrelation and partial autocorrelation plots for the three time series. The ACF plots are on the first row, and the PACF plots are on the second row. The ACF plots point to non-stationarity in the sense of a trend for all three time series. The PACF plots only show partial autocorrelation, a lag 1. However, the ACF plots for the difference time series resemble those of white noise, with the sample autocorrelation being small within the confidence band for lags 1 and higher. The sample partial autocorrelation is small for all lags. Thus, it is plausible that the difference time series to be uncorrelated for all three currencies. In summary, in this lesson, I introduce an example that will be used to illustrate modeling heteroscedasticity. The example is related to the study of the exchange rate between USD dollar and three other currencies. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is modeled on a case study for modeling heteroscedasticity. And in this lesson, I will first focus on the implementation application of ARMA for modeling the conditional mean within this case study. The R code on this slide fits an ARMA model to the difference time series of one currency, being generalizable to all three currencies. I applied here the ARMA modeling to the difference time series instead of ARMA to the time series itself, since the joint ARMA-GARCH model fitting approach in R allows for ARMA, not ARMA modeling. In its implementation, I do allow for the order of 0 or 1 to evaluate whether another differencing of time series is needed. For the AR and MA orders, I allow for orders up to 10. The selected orders are different for the three currencies, but for all three are quite large, particularly for AR order, indicating that the difference exchange rate time series are long memory processes. The rest of the R code is for performing the residual analysis. This code applies again to all three currencies. The R codes for the three currencies are provided in the three different files, but the results will be presented together for comparison in this lecture. The upper plots are the residual plots, and the lower plots are the squared residual plots for all three currencies. The residuals for the euro show some large variability clusters extended over longer periods of time, while the residuals of the Brazilian real presents larger variability clusters over short periods of time. Moreover, the residuals plot for the Chinese yuan presents some extreme values or outliers. Because of these outliers, it is difficult to assess the variability over time. Thus, for these currencies, the volatility shows different patterns, long versus short periods of high volatility and outliers in volatility. Temporal patterns in the squared residuals are difficult to evaluate because of the outliers. Overall, we identify non-constant variance in the residuals for all three currencies. These are the ACF plots for the residuals and squared residuals. While the ACF plots of the residuals resemble the ACF of white noise, the ACF plots of the squared residuals do not for Euro and Brazilian real, indicating that the squared residuals are correlated. Last, I applied the testing procedure for uncorrelated data using the box test R command for serial correlation and for arch effect in the residuals. The R command lines are for Euro currency since the ARMA model has orders 6 and 3, thus using N for the DF of the feet and 10 for the number of legs. These inputs will be different for the other two currencies since the ARMA models fitted for the other two currencies have different orders. The p-values for the serial correlation are large for Euro and Chinese yuan, indicating no serial correlation, but it is small for the Brazilian real. The p-values for the arch effect are small for Euro and Brazilian real, suggesting correlated squared residuals, but not for the Chinese yuan. A potential explanation for not detecting an arch effect in the residuals for the Chinese yuan is that the variability in the residuals present outliers, but otherwise constant over time. We'll explore the volatility of the three currencies in the next lesson. In summary, in this lesson, I illustrated the implementation of ARMA on the difference time series of the three currencies. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on a case study for modeling heteroscedasticity, and I will continue this case study on the modeling of the exchange rate between Euro and US dollar using an arch model. By checking the PACF of the square residuals from the ARMA model fit for Euro, for the currency exchange rate for Euro versus US dollar, we would identify an order equal to 8 or 9 since the first A9 PAC values are outside of the confidence band. Note that we use PACF to identify the AR order for a time series. I consider thus here an arch model of order 8. I'm also using here the simple AR command GARCH from the T-series library since we're considering a simple arch model. The rest of the R code is for evaluating the goodness of fit of the arch model, similar to the residual analysis performed for the residuals of ARMA models in the previous lesson. Note that this is the R code for the Euro-USD exchange rate. A similar code can be used for the analysis of the ARMA residuals of the Brazilian real or Chinese yuan. This is the summary of the fit for the arch model applied to the ARMA residuals for the Euro-USD exchange rate. Recall that the arch order is 8, and thus we have 8 AR coefficients, but also A0, which is the estimate of the mean or intercept parameter. All coefficients are statistically significant since the p-values of the test for significance are all very small, indicating that an order 8 for arch model is appropriate. A larger order arch model may be explored. The tests in the second part of the output are for serial correlation in the residuals and the squared residuals. According to this test, we reject the null hypothesis of uncorrelated residuals, but we do not reject the null hypothesis of uncorrelated squared residuals. This is the output of the summary fit for the arch model applied to the ARMA residuals for the Brazilian real. For this model, I use an arch of order 6. All coefficients are statistically significant since the p-values of the test for significance are all very small, indicating that an order 6 of the arch for the arch model is appropriate. A larger order arch model should be explored. Similarly to the model fit for the Euro-USD exchange rate in the previous slide, we reject the null hypothesis of uncorrelated residuals, but we do not reject the null hypothesis of uncorrelated squared residuals. The ACF plots of the residuals and square residuals resemble the ACF plot of white noise, except for a large ACF value at lag 9 for the squared residuals of the arch model for the Brazilian real. Thus, these plots indicate a good fit. In summary, in this lesson, I explored the implementation of the ARCH model to the residuals of the ARMA fit for the difference in time series for exchange rates for euro and Brazilian real versus the US dollar. Thank you.